Well, welcome everyone to Calculus Notes 1.2. Today we're talking about finding limits graphically and numerically. So first, just a short introduction to limits here. We have an informal description of our limit, and it says if f of x becomes arbitrarily close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is that number L. And here we can see the notation for what we're going to be using here with limits. So this is the limit as x approaches c of the function f of x equals L. So let's kind of look at this graphically and see what we mean. So a limit is the intended height of the function at a given value of x, whether or not the function actually reaches that height at the given x. So I'm just going to draw a curve over here. It can be any curve. And this is going to be our function of x. Now we want to find the limit of our function as x approaches this value called c. Okay, so we just trace this up and we look at the height, or the intended height, of this function at that point. And if we map this over to our y-axis, we get a y value, and that we call L, which is the limit. Okay, so what's happening here is we don't care what this value actually is. Rather, we care at what value are we getting close to as we approach this x value from both sides. Okay, so as we get closer from the left and from the right, what value are we getting closer to? And that's our L value. All right, so let's try an example here. First example says estimate each limit numerically and graphically. Okay, well let's go ahead and just do this graphically first. So here we have the limit as x approaches 1 of x cubed minus 1 over x minus 1. Now we can see from this, when we look at the domain, that x can't equal 1. So you're going to see this a lot with limits, that we're going to say that as x approaches 1, but notice x cannot equal 1. So it's really going to force our thinking with limits here. So let's go ahead and find 1 on our graph. So this is your c value right here at 1. And we'll trace this up. Now in a lot of graphing programs, when there's a hole in the graph, it doesn't actually show it because the limit exists. And when you're dealing with pixels, it's very hard to show where one single point doesn't exist. So we're going to add that in, that there is a gap or a hole right there. And here's the rest of our function. Okay. So what we're trying to do is determine, as x gets closer and closer to c from both sides here, what's the intended height? Okay. What are we getting closer to? And you can see it traces over here to 3. So for this graphically, it looks like L, or our limit, is going to equal 3. So now we're going to try this numerically. And to do this, we're going to use a table of values, just like what we have here. Now, right in the center of the table, we're going to put our c value, which is 1. Now notice we can't actually find f of 1 because it doesn't exist. So we're not really going to worry about anything that goes in this box right here. Okay, we're not going to worry about that for now. What we're going to do is make our x values arbitrarily close to c. Now it's kind of funny because we're going to want to start over here and work our way in, and start over here and work our way in. So this is going to be x approaching 1 from the left, and this is going to be x approaching 1 from the right. So we can start out here with something like 1.5, and then we're going to march closer to 1. And we'll try 1.1, we'll do 1.01, and 1.001. So we're within 1,000th away from our intended c value. Now, of course, you can get smaller than this, but we'll see if this turns out to be good. So from the left, we're going to just do the same intervals, but now going below 1. So here we're going to start at 0.5. We'll jump up to 0.9, 0.99, and 0.999. So again, we're 1,000th below 1. So here you can see numerically our x values are approaching 1. So what we want to do now is figure out what are our y values doing. Okay? So what is f of x approaching as we get closer here? And that's what we're going to try to answer. So we're going to use our table of values for this. So pull out your calculator. Okay, and in y equals, we're going to put in our function f of x. So we have x cubed minus 1, and then divided by x minus 1. Okay, we could graph it, and we would see the same graph over here. Okay, so just to verify that it is the same. But we really want to focus on our table of values now. So because we are choosing what our x values are, we need to set up our table a specific way. So we're going to set up our table first, and we'll only have to do this one time for this lesson. So you can see the table set right here. So you need to push your second button, and then second table set. And you need to change the independent variable to ask. Okay, so if you scroll down, you can hit enter. You can see there it's on auto. And then you can hit enter, and it'll be asked. So it'll be darkened around what you want. Now we're going to go ahead and go to our table of values by pressing second table right here. Now I already have values in here. You may or may not, and it doesn't really matter. We can clear them out by hitting delete. Okay, now we have a blank slate. So we're just going to type in these x values now, and it's going to spit out the y values, or f of x. So 0.5, 0.9, 0.99, 0.999. Okay, so we're just going to record these right here. 1.75, 2.71, 2.9701, and 2.997. Okay, now let's go ahead and try it from the right side. So 1.5, 1.1, 1.01, and that's all it gives us there. So you're going to have to go up and replace another one. Okay, so for 1.5, we get 4.75. For 1.1, 3.31. For 1.01, we get 3.0301. And for 1.001, we get 3.003. So looking at the trend here, as we approach from the left and from the right, what value is f of x getting closer to? And it looks like it's getting closer to 3. And so we're just going to put 3 there as our final answer. All right, I want you to go ahead and try example B on your own. You're going to follow the same steps. You're going to find the limit graphically, just like we did up here. Then you're also going to find it numerically right here. You can pause the video and come back in a second to check your answer. All right, welcome back. Let's go ahead and check your answer here for letter B. Okay, I have here that the limit as x approaches 0 of this function is 2. And you can see this graphically. As we approach 0 from the left and the right, we're approaching 2. Now hopefully you did find that x can't actually equal 0 in the domain, because that would give us 0 in our denominator here. So should have this open circle right there. Okay, so graphically it looks like L is 2. When you try this numerically, again you should have 0 here. I decided to choose these values. Okay, you can choose whatever you like as long as they're getting closer from the left and closer from the right. And then if you look at these, 1.99, so on and so forth, and 2.00, they're all going towards 2. That's how you get the limit of 2. For our next example, our function looks a little bit funny. So we're just going to define f of x as 1, where x does not equal 2, and 0, where x equals 2. Okay, so right here at x equals 2, we know our function equals 0, because it tells us. And we know where it doesn't equal 2, our function equals 1. So it's going to look like this. Okay. We are going to put an open circle right there, because at 2 it jumps down to 0, and then after 2 it jumps right back up. Okay. So in this we want to find the limit as x approaches 2 of our function f of x. Now this example is really going to highlight our key concept here, that the existence or non-existence of f of x at x equals c has no bearing on the existence of the limit of f of x as x approaches c. In other words, it does not matter what's happening at x equals 2. All we care about is what's happening going up to x equals 2. So graphically, okay, if we were to trace along this as we get closer and closer, what is the value we're getting closer to? Well, that value looks to be 1 from the left and the right. If we were to try this numerically, we'll put our c value right in the center there. And we can pick some values that get larger here, and then we'll pick some values that get smaller. Okay, so if x is 1.9, what is f of x? Well, if we look at our function, anything other than 2 is going to yield 1. So we know all three of those equal 1. When x equals 2, we know f of x equals 0. And if we're at 2.01, we're right back to 1. Okay, so again, as x approaches 2 from the left, and x approaches 2 from the right, what's happening to our f of x value? Well, f of x is approaching 1 from the left, and then from the right, f of x is also approaching 1. Notice, even if we made even smaller difference in here, 2.0001, we're still going to get 1. And so our limit here, as x approaches 2 of f of x, equals 1. So if the existence or non-existence of f of x at x equals c has no bearing on the existence of the limit of f of x as x approaches c, what does create a non-existence of a limit? And that's what we're going to talk about in this section, is limits that fail to exist. So there are 3 common types of behavior associated with the non-existence of a limit. The first one is that f of x approaches a different number from the right side of c than it approaches from the left side. Okay. The second one, f of x increases or decreases without bound as x approaches c, thus yielding a non-real number. Or f of x oscillates between 2 fixed values as x approaches c. So we have 3 examples here that are going to show these 3 types of behavior. So for our first example, it just says show that the limit does not exist. So it's finding the limit as x approaches 0. So here's c equals 0 of the absolute value of x over x. Now in this case, it looks like x cannot equal 0. Okay, because then we'd have to divide by 0. So graphically, if I were to look at this, as I approach C from the left, this looks like it's giving me an L of -1. But as I approach C from the right, it looks like it's giving me an L of +1. Okay, so that right there is going to tell me that the limit doesn't exist. If we look at our table of values here, we'll put 0 here in the middle. Get larger and then get smaller. Okay, if we examine our equation, so it's going to be the absolute value of x divided by x. So when x is negative here, it's automatically going to make the numerator positive, but the denominator is going to stay negative. And since it's the same thing, we're going to get either positive or -1. So if x is negative, then we're going to get a -1 right here. Now if x is positive, then it's just going to stay +1. So you can see numerically, from the left side, f of x is getting closer to -1, and from the right side, f of x is getting closer to +1. So for our answer, we want to explain this a little bit. We want to say the limit doesn't exist because f of x approaches a different number from the right and left of C. So you do want to give a little explanation, and that highlights our first point right up here. All right, let's move on to our second one. Example B. Here we have the limit as x approaches 0 of 1 divided by x squared. So you can see here the graph of 1 divided by x squared. And again, because pixels have a thickness, a lot of times your graphs don't become very clear. But we would see that there is an asymptote right here, that our y values can never go below 0. And we'd also see in the domain, because of the x squared, that x can never equal 0. So graphically, what's happening as we get closer to our c value of 0? Well, from the left side, it looks like this graph is just going to keep shooting up to infinity. And from the right side, the same thing. Okay, so even though they're going in the same direction here, this is increasing without bound. So graphically, it looks like our limit doesn't exist. Let's go ahead and show this numerically as well. We'll put 0 here in the middle. And just standard, I usually use these. Okay. And again, we can use our table of values if we're not good with using these numbers here. So 1 divided by x squared. And then again, I'm going to push second table. Type in -0.1, -0.01, -0.001. Okay, so we get 100. And then we get 10,000. And we get 1e6. So we're going to come across these exponents a little bit here. 1e6 just means add 6 zeros after the 1. So 1, 2, 3, 4, 5, and 6. Now, will we ever get to 0? Okay, we said no, we won't, because it's x over 0. However, that is not what causes this limit not to exist. Okay, we'll move on to the right side here. 0.001, 0.01, and 0.1. Now we get 1e6 again. So that's 1 with 6 zeros. .01 gives us 10,000. 0.1 gives us 100. So you can see as we f of x from the left side is increasing without bound. So it's going to get larger and larger and larger. It goes to infinity. Here, from the right side, the same thing is true. So f of x is going to increase without bound, going towards infinity. Now it turns out infinity is not a real number. Therefore, the limit does not exist. So we're going to write the limit doesn't exist because f of x increases without bound as x approaches 0. So this one was our second type right up here, increases or decreases without bound. We're going to look at a very interesting function, sine of 1 over x. So this is what it looks like on my computer. We just kind of, the graph comes down, goes up to 1, goes back down to -1, and then as we go through here, it just starts going crazy back and forth between 1 and -1. And then as it gets a little bit past 0, the same thing happens until it sort of starts to level out and keeps on going. So we have this oscillating behavior between 1 and -1. And that is going to make the limit not exist as x approaches 0. Now for these ones, we're not actually going to use a table of values. You can look in your textbook if you're interested about that, but that's going to be outside of what we're going to be doing here. So for now, you can just say limit doesn't exist because the function oscillates between 1 and -1 as x approaches 0. And you can leave it at that.